Today we're going to be talking about moment of inertia, the tensor for first a rigid body of particles, and then a continuous mass distribution, and also get to principal axes. So this continues from where we left off last time. If you recall, for the rigid body of particles, made of discrete particles, we'll call them epsilon I. So here's like a mass over here in this figure. There's mi. I don't know why it doesn't show 3 axes for the rigid body, but there it is. That's the B frame. You could view this as kind of rotating that way, or also there is some angular velocity vector of the B frame with respect to the inertial I frame. The total angular momentum of the system is what's going to enter the dynamic equation. So the total angular momentum of the system about its center of mass, which we called G. Here is that. And the way we wrote it last time, so we're assuming we have a collection of n particles, so the summation goes, I goes from 1 to capital N, mi, location of particle I with respect to G, so Rig, cross, and now the inertial vector, inertial velocity, which is the angular velocity cross Rig. So we have the summation. We want to write it in the form of something times I omega B. So the angular momentum is going to be proportional to the angular velocity. It turns out what this thing is, unknown in the parentheses, is going to be a tensor. Or when you write it within a specific set of axes, it'll be a matrix, a 3x3 matrix for a 3D rigid body. So to be able to write this cross product in a way that it looks like the second line down here, we need to do a little bit of a mathematical aside on writing the cross product in matrix form. And this is from page 641 in Appendix B of the book. So if I have a vector, vector A cross vector B, these are 3 vectors, and let's call that C. So C equals A cross B. Now let's say that they're all written in the common frame. So all written in, let's say, B frame components. So A, write it this way, is A1, A2, A3. It has the 3 components. The B vector has components B1, B2, B3 in the B frame. And vector C, same deal, C1, C2, C3. And we put the little subscript B to remind us these are all B frame components. So C1 is in the B1 hat direction and so on. So we'll write this cross product completely in terms of the B frame. This would be C equals, and we'll write A cross, that's a matrix, times the column vector B. So what is going on here? This first thing is a column vector. This last one is a column vector. And this A cross, it's a 3x3 matrix. where I don't know what the book may call it. It may call it the cross product equivalent matrix. So A cross. You take the components of A, we know the components of A are A1, A2, and A3, and you form those into a 3x3 matrix, which has zeros along the diagonal. And then this is negative A3 up here, A2, negative A1, and then this is a skew-symmetric matrix. So this is A3, negative A2, and A1. So this is a 3x3. In terms of its mathematical properties, it's a skew-symmetric matrix. What does that mean? That means that if you took A cross transpose, you would get negative A cross, which would also be the same as the matrix of negative A cross. Okay. So if we were to write this completely in terms of these matrices, we would have C1, C2, C3 equals, then we have this matrix, 0, negative A3, A2, A1. The diagonal has zeros, and then we just sort of, you flip about the diagonal and change the sign because this is skew-symmetric. There we go. This is all in the B frame, and then this is B1, B2, B3. For just general vectors, C, A, and B. So what happens on the right-hand side here is this works out to give you what the cross product would give you. And maybe you've memorized a different way to get the cross product, but this also works. So we have written the cross product in terms of a matrix, and now we're going to apply this to write H up here in terms of omega. So let's just go ahead and do that. What we'll end up with is that H equals some matrix times omega. So let's just write that. H equals, let's just write what we have up above. We'll have a sum from 1 to n, mi, and I'll use a property of the cross product. I've switched the order of this second cross product, and that's where I pick up this negative sign. And now we will write this cross product using exactly what we had up above. So what would this be? This would be R, I, G cross. Then let's write everything in terms of the B frame components. So this is B. That's a 3x3 matrix with entries given the way we would expect them, times the column vector of omega, also written in the B frame. Okay. So what do we have now? We've got this summation 1 to n mi times, and let's move the negative sign over here. So we've got negative mi times r I g cross times r I g cross I omega b. So what we have a 3x3 matrix times a 3x3 matrix. Okay, and the product of a 3x3 matrix times a 3x3 matrix is another 3x3 matrix. So this is a 3x3 matrix. We will include the mass in there, and so then we will define something that we call, we'll define I G of the ith particle and in the B frame. So if you want, I'll write it over here. This is a 3x3 matrix that equals, it's defined to be negative the mass times this product of two matrices, following the rule up above of taking a column vector and turning it into a 3x3 matrix. And this is all in section 11.2.2, if you're interested in following along in the book. So this is, we will call this is the moment of inertia matrix for particle I. Particle I. So of course we have a sum of these, I, H, G equals the sum from 1 to n, the number of particles, I, G, superscript I, B. And so we have this summation of things that do not depend on omega, all times the vector omega. I guess for consistency, I need to write that over here, we're writing the angular velocity, angular momentum vector also in terms of the B frame. So this thing is it's the sum of the moments of inertia matrices of each particle. So we'll call this, we'll just drop the superscript I. So we might call it the total moment of inertia of the collection of particles. Which are all rigidly attached. This is I, G, respect to the B frame, and it is the sum from 1 to n of all of the moments of inertia of each individual particle. Okay. So then we're left with I, H, G, the angular momentum, written in terms of the B frame, equals a 3x3 matrix, right? A sum over here, this sum of 3x3 matrices is also a 3x3 matrix. And then this is times the angular velocity written in the B frame. So we have what we were looking for up above. Now, we can write an expression. Let me just repeat, for each particle, because this is related to your homework problem 3. For each particle, right, we've got the moment of inertia, and maybe it's not with respect to G, it's just with respect to some point. I'm using G here as an example, but you could write this with respect to the origin. And this is what? Mi times, you could write it this way, negative Rig cross B frame. Rig cross. Now, if you work out the matrix multiplication, you'll get something. And I'll just give you what the result is. So if you work out the matrix multiplication, you get something that looks a little bit nicer. This is, I've got the mass out in front. Then we have the magnitude of Rig squared times the 3x3 identity matrix minus, now it's Rig B times Rig B, and then this T, this is the transpose. We write Rig as a column vector, let me just say with this is the 3 by 3 identity matrix. This is a column vector. And if you take the transpose of a column vector, what do you get? You get a row vector. A column vector times a row vector is going to be a 3 by 3 matrix. Right, and so RIG, this is just the location of particle I with respect to some point, like G. So this is going to be like XI, YI, ZI for that, you know, the ith particle. Okay. So then you could apply this directly to that homework problem 3. Let me give you another useful result before we discuss that example. This Oslo, no, also useful. This, I'll just give you the result of the parallel. This is the 3D parallel axis theorem. And this is on page 498. But the result is if you have, let's say you've got your center of mass for a collection of particles, and then some other point Q, and here's the location of Q with respect to G. So Q is some other point on the rigid body. And suppose we want to write the moment of inertia tensor with respect to that point Q rather than G. Then the moment of inertia about the point Q is the moment of inertia about the point G plus mg, that's the, right, this is the mass of the rigid body. So if it's made up of a collection of particles, it's the total mass. It's times this vector RQG, magnitude squared, times the 3 by 3 identity matrix, and then RQG times RQG transpose. So this reduces to the usual 2D version of the parallel axis theorem that you might be familiar with from like sophomore dynamics. This is equation 11.57. So if you were following along in the book. Okay. Now I did want to show you, give some ideas to what you would do for that collection of, for a collection of particles. So let me insert a figure here. Let me go to there. Okay. Here's a situation. This is an example. This is an example collection of particles that are rigidly connected. In this case, to like a massless wire frame. And we could label these. It's probably convenient to label this one at the origin. This is particle 1, over here is particle 2, then over here is particle 3, and up here is particle 4, which means if we were to write location of particle 1 with respect to the origin, and all in the B frame, well, it's at the origin. So this is just a column vector of zeros. If we were to write where's particle 2 with respect to the origin, it's only along the first axis, the B1 axis, a distance A, and then everything else is 0. And hopefully you get the idea, right? R3 is it's at 0, B 0 with respect to the body fixed frame. R4 0. That's the unusual one because you go a distance. This is a parallelepiped, so it's A in the B1 direction, B in the B2 direction, and then C in the B3 direction. So once you've got this far, you can do all kinds of things, right? You could write the moment of inertia matrix with respect to the point O. So the total moment of inertia of this system with respect to the point O, and written in the B frame, it's the only frame we're given, would be you take the sum from 1 to 4 of each individual particle's moment of inertia with respect to the point O. And the moment of inertia with respect to the point O is going to be the mass of that particle times its location, basically the distance squared of that particle from the point O, times the 3 by 3 identity matrix, minus R I O times R I O transpose. The first one is, since R10 is the 0 vector, that one is just going to be a matrix. R10 is just going to be a matrix of a whole bunch of zeros. It doesn't even matter what the mass is. Okay. What about particle 2? Particle 2, so this is I2O. Well, its distance is A, and so its distance squared is A squared. So take A squared, and what's its mass? Just M. So we have M, and then it's A squared, oops, not A2, A squared times the identity, 3 by 3 identity matrix, minus AOO times the transpose of that, AOO. You can work this out to give you, it'll give you the mass M times everything is zeros except for there's A squared, the 2 slot, and the 3 slot, etc. And then you would just add all of those up, like up here, this boxed equation, to get the total moment of inertia matrix for this system with respect to the point O. Now, how would you do D, part D of homework problem 3? If you wanted to get the moment of inertia about the center of mass, you'd first need to calculate where the center of mass is. And hopefully you remember from last time, right? What is the location of the center of mass? The location of the center of mass with respect to our given origin would just be 1 over the total mass. What's the total mass here? We've got 3 that are mass M, and then particle 4 is mass 2M. So we've got 1 over 5M. And then just the MR10 plus MR20 plus MR30 plus 2MR40. And you can work that out to get the location of the center of mass. Once you do have that, you can use the 3D parallel axis theorem to find out what's the center of mass. You could actually, you rearrange this to solve for IGB, given, in this case, your IQB. Q is another point on the rigid body, and for this case, you would use the point O. So you could, you don't have to recalculate all of those matrices. It should be very simple to get the moment of inertia matrix with respect to the center of mass. And then if you were given some, whatever that matrix is, the moment of inertia with respect to the center of mass, if you wanted to get the angular momentum, this would be this times, I omega b, written in the B frame, where, that angular velocity written in the B frame is going to have components, omega 1, omega 2, omega 3. While it's instructive to look at the idea of a rigid body of particles, eventually we want to work with continuous rigid bodies. So that means you go to a continuous limit. So what do I mean there? We can think of discrete masses that are, connected, each one to the other, in some rigid array. But then we need to go to the continuous limit. Meaning a continuous mass distribution. And in this case, we would have, for example, a block of material, and it's this is our fancy B describing the body. There are infinitesimal elements within it. Let's see, call that dV, and this is made up of dx, dy, dz. Those are the sides of the cube. Let's say this is dx, and then this is dy, and then height dz. This is a volume element, an infinitesimal volume element. So instead of doing a discrete sum over masses, right, this would be a sum, this is the summation symbol, a sum over masses. We go to the continuous limit and we have a integral over volume elements. So one important thing would be, you set up some, let us set up an origin for some body fixed frame. And maybe it's an origin that's just easy for doing computations. So there's our origin. And we would write the location of each volume element. And each volume element would have some kind of density associated with it. So here's like our R. We might write it as rho, or we might write it as mu, but this is a mass density, meaning this is the mass per unit volume. And it often the assumption is made that just to simplify computations, the assumption is made that it's uniform density, but this doesn't have to be the case. You could have a material that varies in its density. So this thing could vary throughout the body. I'll give you an example. The Earth, the density of the Earth is not uniform. On the surface, it's got a certain density, roughly the density of rock, about 3 grams per cubic centimeter. As you go further down, the density gets larger and larger. The core is much more dense. It is made of iron, which is far more dense than the dirt outside. But, you know, a piece of wood or a piece of steel, you can often get away with assuming it's constant density, even 3D printed objects. All right, so we'll be doing some integrals instead of summing over masses, because doing integrals is more efficient. So once we have a continuous mass distribution, then how do we define these things? The moment of inertia matrix with respect to a body fixed frame is going to be, you know, in 3D, this will be a triple integral over the body. And instead of individual masses like mi, we've now got the density and the location of each mass. But we've got the same kind of calculation here, RB transpose. And this triple integral is over, you know, dv, but we're writing out dv as dx, dy, dz. So there's how you would do this for a continuous mass distribution. Now, if we make the assumption that we've got continuous density, so if density is constant or uniform, we'll just say rho. So the density is just one value throughout. We can pull that out of this equation. So pull out the density, and then we've got this still a triple integral over the body. And if you work out what this matrix is, so if each point R we describe as X, Y, and Z, let me be careful and write in the body fixed frame. So this is a triple integral over a, what's R squared times the 3 by 3 identity. This is X squared plus Y squared plus Z squared. X squared plus Y squared plus Z squared. X squared plus Y squared plus Z squared. Oh my. Everywhere else is zeros. Minus, and then if you work out what this R times R transpose is, you get a 3 by 3 matrix that looks like X squared, XY, XZ, XY, Y squared, YZ, XZ, YZ, Z squared. Okay, and what are we integrating over? dx, dy, dz. Okay, if you work out what each of these things are, what do we get? We get I, G, in the body fixed frame, density, and I'll do my triple integral again over the body. And I'll just, you know, subtract these two matrices. What am I left with? I have y squared plus z squared up here in the left-hand corner, and then negative xy, right? Because there's that negative sign. And then negative xz. And let me just carry this through. Put the little end brackets there. X squared plus y squared. Now, each of these elements, so put the density back in there. We also, it's often, it's common to write the entries. So we have the entry I11, and then we have I12, I13. But notice that I12 is the same as I21. So I'll just write I12 over here as well. And then we have I22, I23. This is I13, because right, negative ZX is the same as negative XZ. I23. So really, we only have 6 independent elements. And so it seems. It may be even beyond that. If you're following along in the book, this is equation 11.22. What do these different parts of the 3x3 matrix mean? So here's some meaning, interpretation. I11, what is this? Density. And then this triple integral y squared plus z squared dx, dy, dz. This is it's a measure of how difficult meaning how much inertial resistance there will be to rotate about the one axis, or if you want, the x-axis, the B1 axis. So let's, let me just, here's a sketch of a rigid body. I'll often just write some kind of block looking thing. And here are, there's, let's have a frame. Here's our frame, and let's say it's already centered at the center of mass. Okay, so we're talking about rotation out the B1 axis. I11 is a measure of how difficult it is, how much inertial resistance there is to rotate this body about the B1 axis. It's a rotational version of mass. The mass of something is a measure of its inertial resistance to translational motion. In terms of nomenclature, right, I22 and I33 are, similar. They're measures of resistance for rotating about the number 2 axis or the number 3 axis. These things that are I don't like saying I, Captain. Let's just group these together. I11, I22, I33 they are themselves called the moments of inertia, and they're scalars, and they're the diagonal elements of this 3x3 matrix. The off-diagonal elements so that would be the only, there's only 3 independent ones, I12, I13, I23, are sometimes called products of inertia. And they're harder to interpret. I don't have a good idea about how they're interpreted. But there is something special about them. You can actually find a frame. There is a body fixed frame in which these products of inertia disappear. In fact, maybe we should make a note of that. So I'm going to do some mathematical note now. So this is just noticing something about the matrix. Notice that and sometimes I'll just call it the inertia matrix or moment of inertia matrix. It is symmetric. So if you have the moment of inertia, and it's about any point, Q, if you take its transpose, you get the same thing. So it is a symmetric matrix as a matrix. It also happens to be positive, definite. Left as an exercise to figure out what all that means. But it's good to know. We will use the fact that it is a symmetric matrix to simplify things. So here's another mathematical aside. I want you to consider the properties of a symmetric matrix, a 3x3 symmetric matrix. So this is a symmetric 3x3 matrix, and I'll call it S. Okay. Positive semi-definite here will show up. And that if you were to look at its eigenvalues, I assume you know how to get eigenvalues. All of its eigenvalues are real, and in fact, positive. Let's call them lambda 1, lambda 2, lambda 3. There are corresponding real eigenvectors. This is true for any symmetric matrix. We were just now talking about 3x3 symmetric matrix. So I'll call the eigenvector corresponding to the eigenvalue lambda 1 is E1. And I put a hat on them just to say that we've already normalized them to unity. So these are unit vectors. And in fact, they're all orthogonal. And being normalized, so equal to unity, means that they are orthonormal. What does orthonormal mean? It means that if you take EI and dot it with EJ, the usual dot product, this is going to be the Kronecker delta. So it's 1 if I equals J, and it's 0 if I does not equal J. So that means they are orthogonal to each other. Now we can actually find the directions. In fact, it's these eigenvector directions. These eigenvector directions form a new body fixed frame. So E1, E2, E3, that collection of vectors forms a new frame in which we can describe the matrix. This is like the theory of similarity matrices. So if we, how do we do that? We do a linear transformation via a matrix P. So we can transform to this frame by another matrix. This is a linear transformation matrix, P. What is P? P is going to be a 3x3 matrix where we write these vectors, E1, E2, and 3, but write them as row vectors. So that's why these little dashes going horizontally mean we write the eigenvectors as row vectors. Okay. Then if we were to take P, S, P inverse, and what is P inverse? Since it happens that because E1, E2, and E3 are orthonormal, that P inverse is equal to P transpose. So P, S, P transpose is, it's the basis in which we have the simplest representation of this matrix S, in which it's just a diagonal. Maybe you've seen this way of writing things. Diagonal, lambda 1, lambda 2, lambda 3. So we would say this is it has the same physical content. This is the matrix S transformed into its eigenbasis. Now, how do we apply this to our 3x3 moment of inertia matrix? So this can be applied to find the best body fixed frame, which I'll just go ahead and tell you now is called the principal axis frame. So if I have let me sketch over here a kind of general rigid body, and suppose I've just chosen some frame, B1, B2, B3, some initial body fixed frame that was good for making my calculations. And this could be centered at some origin or maybe at the center of mass. I'll just put the center of mass just for kicks here. I've got the moment of inertia about the center of mass with respect to this B frame. And this will be, you know, some set of numbers. It's a symmetric matrix. You should probably check that you have a symmetric matrix if you were to do calculations. Otherwise, you've done something wrong. Once you've got this, you could solve for eigenvalues. And we'll call those eigenvalues I1, I2, I3. These will be called the principal moments of inertia. They're the moments of inertia. Remember I11, I22, I33. Those are the moments of inertia for some general frame. These are the principal moments of inertia. They are the moments of inertia in the principal axis frame. So these are the eigenvalues of your matrix here, and there are corresponding normalized, which just means you might have to rescale your eigenvectors to make them their length equal to unity. We have normalized eigenvectors, and I'll just use the same thing I wrote up above. E1 hat, E2 hat, E3 hat. These actually correspond to directions, so I'll write them in here. This would be E1, this is E2, and E3. They're special directions, which instead of using just the B frame, I'll say that the B frame is centered at our center of mass G, and then it has a triad that respects the right-hand rule, B1, B2, and then B3 must be B1 cross B2. We also have a principal axis frame, which is more convenient to use. So we'll write that as B sub P. just like the book does. And it's got directions E1, E2, E3. You need to be careful. You need to check that E1, E2, and E3 obey the right-hand rule. So you might have to rearrange the order of your unit vectors. Right, so this is, you need that E3 equals E1 cross E2. So system of vectors is a right-handed coordinate system. Or let's say right-handed coordinate frame. You need that. Then these E1, E2, and E3, just like the eigenvalues are called the principal moments of inertia, these things are called the principal axes. And then this frame is called the principal axis frame. Your transformation matrix, you could write it as it's a transformation matrix from the B frame to the BP frame. And we write E1 as a row vector, E2 hat as a row vector, and E3 hat as a row vector. Once you do that, then the moment of inertia in the BP frame is P I G B P transpose, and that is equal to I1, I2, I3 with all the products of inertia going away. So the products of inertia are just sort of an artifact of not being in the best frame, a principal axis frame. Right, what did we say? BP is the principal axis frame. Simplest, simple is spelled with an I. It's got the simplest matrix representation, inertia matrix representation. It also has a, and this is all in section 11.5 of Kasdan and Paley. These principal axes have a physical interpretation in that the if you were in empty space, it's possible to have pure rotation around a principal axis direction. So principal axes are the only directions in which you could rotate the body, only directions, let's say axes, about which one could get pure rotation of the body. If you take some other direction and you try to rotate the body about that, you'll notice some other weird effect happening, which we'll eventually talk about. So any three-dimensional shape is going to have principal axes to it. Let me show pure rotation. Right here is pure rotation. This is a block, maybe much like your cell phone. And there is we've got the principal axes labeled here, 1, 2, and 3. So you can have, if you get this thing spinning initially about one of its principal axes, you can get pure rotation about that axis. If you start something off spinning about a direction that is not a principal axis, you will get what looks like tumbling and other types of motion. But we'll be talking about that more later. I just wanted to give you a preview of what the physical significance is for these principal axes. Okay, I think that is it. We'll say more next time about continuous mass distributions, maybe even calculate things like the center of mass. And for simple things like flat plates, and then go into more rigid body dynamics, actually use these things like the moment of inertia tensor.